Hey there, my name is Alejandro. I work back for day 321 of me doing daily LeetCode challenge after 20 years worth of green contributions here on GitHub. So today's one is for June 2nd, 2025. Without further ado, let's get straight into it. In the meantime, by the way, this is my friend Howard.
Hello.
Hello, Howard. Today we get a LeetCode hard problem 135 candy.
They're giving you a hard right off the bat, dude.
It's gonna be like yesterday. If we have a combinatorics month, this is gonna be rough. By the way, fun little trivia fact. Today we went bouldering, and I hurt the crap out of my left knee. I'm now walking with these crutches over here, and I'm just stuck on the sofa. And these guys are here for emotional support. And this money's taking a nap. Okay, well, it's a good thing I got a LeetCode hard. I'm not getting off this couch anyway.
Let's figure it out.
All right. There are n children. Oh, and you're going to be good at these types of problems. Yes, I'm so happy. There are n children standing in a line. Okay.
Okay.
Each child is assigned a rating value given in the integer array ratings. I see. We teach these children on fairness right off the bat. You're better than this kid. You're giving Oh no. You're giving these candies subjected to the following requirements. Okay, at least each child must have at least one candy. This is good. There's some fairness. Children with a higher rating get more candies than their neighbors. Return the minimum number of candies you need to have to distribute the candies to the children. Oh, okay. We can just build like a tree and like what's the deepest node, right?
Yeah.
It's like you create a topological ordering of the children.
Is that right?
Or wait, is it just the number of unique rating value? Okay, let's look at an example. 102, 5. Can allocate to the first, second, and third child with 2, 1, 2 candies respectively. Oh, wait. 102. The higher get more candies than their neighbors. Oh, just their neighbors. So this guy must have more candies than this guy. This guy's have more. Oh,
interesting.
wait, with a higher rating. Does that mean the higher rating than their neighbors, then they get more candies than their neighbors?
I see.
I still think I can make this like a tuple sort graph, but I wonder if it's necessary, right? To the first, second, third child with 1, 2, 1 candies respectively. Why? The third child gets 1 candy, satisfies the above two conditions. Each child must have at least 1 candy. Children with higher rating get more candies than their neighbors. Yeah, this guy's not higher rating than any neighbors.
Equal, yeah.
Oh, but it must be more candy than the other one, which might actually need more candy. So that I think I can just tuple sort this thing. Or it's like for each index I. For I, comma rating. Here we can just do for I in range 1 length of ratings minus 1. I'll handle the first and last case. Or maybe I just add like, infinity on both sides of the array. Right? Make ratings equal to float of infinity plus ratings plus float of infinity.
I'm interested to see what you're cooking right now.
Alright. So that way, like, if there's infinity as your neighbor, you're not gonna have a higher score than that guy.
Yeah.
So we'll say
with like the topological
rev is equal to ratings at index I minus 1. Next is equal to ratings at I plus 1. Alright. And cur is equal to ratings at index I. So really I can just say rev cur next equals ratings of I minus 1, ratings of I plus 1. I could really use string slicing here. Yeah. Rev cur next equals ratings of I minus 1 to I plus 1 plus 1. That's fine. It doesn't really matter. Okay. here we're just gonna have an adjacency list. There's gonna be, so what are the children? It's just gonna be indices of the ratings array. So here we'll say n is equal to length of ratings. Alright, adjacency list will be, oh, it'll be this. That's fine. Cur index equal to I minus 1. Actually, you know what? I'll just do this. We'll just say prev is equal to this if I greater than 0, else float of infinity. Let's just make our life simple. This is if I plus 1 is less than n, else float of infinity. Sweet. There we go. Let's not make our life complicated. Right, now this will be just a list for I in range n. Okay. If so each child must have at least one candidate. So what would I want at the beginning? The ones that have no so what should be the dependency ordering? If a child has higher rating, right?
The dependencies are very limited, right? It's only based on the two neighbors.
Alright. So it's like if the kid above you should be the one getting less candies, probably. Right. Right. The deeper you go, the more candies you need. Right? And so then you basically get a depth of each child. If cur is greater than prev, cur needs more candy than
Oh, so you're just creating like the top, the
yeah,
graph
index
of
I,
dependencies,
then
and doing topological sort.
Yeah, I minus 1. So here we'll say adjacency list of I minus 1 dot, here we'll make this a hash set for now, whatever, dot add index I. Cur greater than next. Here we'll have in degree is equal to 0 times n. I minus 1 now points to I. So in degree of I plus or equal to 1. Here we'll say adjacency list of I plus 1 points to I. So its in degree is now augmented by 1. Right? Now we'll say run a tuple of sorts, but get the depth of each node, I guess. The depth. I don't know how I like this. Basically, it's like I want to run BFS from the Q is equal to DAC. Or here I should say printf string adjacency list. Or what? Oh, I should do this now. Yeah, now that I don't have two sides of the array, I should definitely go through every single thing in ratings. Yeah, okay, so 1 has 2 that it's bigger than. So here's like 1 candy for this child. This child Okay. It's like if I built a graph, so 0 and 2 point to 1. Wait, this doesn't even make sense. Why the heck does 1 point is... Oh, these are indices. We can make it like this. Yeah, so index 1 points to index 0 and it points to index 2. Right? So this guy only needs 1 candy. But each of these two will need at least 1 extra candy. Okay. Now for this, it says index 0 needs more candy than index 1. No. Index 1 needs more candy. Should I do it the other way? Let me just print. Maybe I should draw the edges the other way. Print f string in degree line range n. Print f string I in degree of I equals print is 1. So I'm saying this guy, but I really should have these guys point to this, right? I don't know. But it makes sense. The one with an degree of 0 just needs 1 candy. These guys need 2 candy. Like, can I just do something as simple as turn n plus sum of in degree dot values? Did I misspell this?
In degrees dot value, it should be just in degrees.
Oh,
right?
it's an array, not a dictionary. I'm dumb. I forget that I do that for optimization now, but I'm so used to making in degree a dictionary. Okay, so this accepted for these two test cases. Either we fail something. I don't think we're gonna pass because it's a LeetCode hard. There's gonna be edge cases up the wazoo.
So sad.
Alright, let's see this boy. One, 3, 2, 2, 1. Okay, so let's see. 0, 2, and 1. Okay. This guy has an degree of 2. It's pointed to by this guy and this guy. This guy has an degree of 1. It's pointed to by this guy. Okay, but just because it's pointed by these two, basically, I need to get each node's depth times n. Q is equal to collections dot deck 0, comma node for node in range n if in degree of node equals 0. While Q, and here we'll have a visited set of Q. Here we'll say depth from a node is equal to Q dot pop left. Assert depth of nodes equals -1. Or maybe I could make this a min heap. Or max it. Depth of node is equal to -1. Oh, wait, could I just do something as simple as n plus sum of in degree of node and 0 for node in range n. Yep. Just comment this out for now. So passes for these 2 test cases. Let's see what else we fail. Okay, we failed something else. That's good to see. Okay. 1, 1, 1, 1. Something bigger than it. This guy's nothing bigger than it. It's tripping. Oh no, it's about if you have something smaller than you, right? So this is something smaller. This guy has something smaller. This guy has nothing smaller. This guy has something smaller, something smaller. So these guys get 1 candy, 2, 3, or 1, 2, 3, 6, 7, 10, 12, 13. Yeah, this guy gets 1 candy. So yeah, I just want to make it the tree here. Can I do a multi-source BFS? Yeah. This is Koseki. Okay, if main visited, depth equals. That's my bad. Okay. Everything's at a depth of 0 until proven otherwise, right? So 1, 2, 1 is 5. Turn n plus sum of depths. Okay. 1, 2, 1 is 4. That should be really 2, 1, 2. Oh god. Maybe I should make the edges the other way. Oh, nice one. I think it just depends on like increasing channels. Okay, I'll try not to talk too much. So this usually means DP, re or divide and conquer. Might be. Ouch. There we go. Well, 28. This guy needs more than this one. 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 This guy needs more than this one, right? Needs more than this one. So you should point to something if you need more candies than that one. Index I needs more candy than pref. Index I points to I minus 1 because it needs more candies in it. Right. It's the ones that so that means the ones within degree 0 are the ones that actually need the most amount of candy. But does this form a DAG? Because then I could just DP, right? That's the thing. This is gonna make a direct acyclic graph, right? There's gonna be a DAG. There's not gonna be cycles, right? Even as something like this, right? This guy needs more candy than this one. This guy needs more candy than this one, right? You essentially have a node here, a node here, and a node here, right? This points to here. This points to here. There's no cycle. Def dp of r. if adjacency list of I return one candy, right? Otherwise, need more candy than anybody else, so just one candy. Otherwise, grab 1 plus min of dp of name node for name and adjacency list of node. No, not min. Max, right? Return sum of dp of I in range n. Okay, submit. And there we go, bada bing bada boom, completion history 321 days, consistency is key. See ya tomorrow. Okay, a nice DP solution to do this. Beautiful. Okay, sweet. Here we can just do this. Yeah, and here we can just do in degrees useless. Oh my gosh, this is a way simpler problem than I thought. Memo equals this. There we go. And sum of dp of I for I in range n. Okay. This will be a list. Yeah, this is a fine way. Here this will need to be append. This will need to be append. Right, so this works. 106 still here. Let's get rid of the adjacency list stuff. Plus A for name and adjacent indices of name whose ratings are small. For neighbor index case 1 left neighbor. Index and memo. Into a memo index. Go back to the say both adjacent pairs. As possible, of course. Okay. Index I needs must be at least 2 satisfy first condition. Is equals to 1. Two. If res less than case 1, is case 1. If index is 1 is less than n, neighbor is equal to ratings plus 1 is less than rating. Case 2 is equal to 1 plus dp of index plus 1 if res is less than case 2 is equal to case 2. Right? Remove index is equal to res, return res. Right? Something like simple as this. guy? Yeah. So now we don't need all this busy work. Sweet, let's submit. Okay, we're still kind of slow, but we're at least a little faster. Maybe it's because we're looking at the left and right indices, and so therefore you could like reduce the time by half, and like that's about it, right? Like we're at 39 ms, people can reduce it down to 17. You just look at longest chain kind of a thing, right? Maybe it's like, you look at this, right, and you're like, I must give only like one candy. It's like, oh, I'm bigger than this one, so it's like 2 candy. But like it's the both ways, right? I like this solution. It's O of n at the end of the day, right? Because it's like there's n possible indices. This is O of 1, O of 1, O of 1, O of 1 is O of n. So it's an O of n solution, which is just a nice solution. It's a LeetCode hard. We solve it in a nice way. Okay, so nevertheless, as always in my videos, a quick recap of ISO will solve a problem. So for this one, I actually realized there's a much easier way to go about things. I was trying to do like, a topological sort, have an adjacency list, and so on, until I realized that, yes, you can treat this problem like a graph problem, but every node can have like at most 2 neighbors, and also the graph forms a directed acyclic graph, so you can just keep dynamic programming your way through this. And DP is usually good for minimization, maximization problems, or any kind of optimization problem. So it was very convenient in this case. So we have n children standing in line. Each child is assigned a rating value in ratings, which is given here, index I. This child I, and its rating is ratings of index I. And you're giving the candies to these children subject to the following requirement. Each child must have at least 1 candy, and children with a higher rating gets more candies than their neighbor, right? For example, here, the first child has a rating of 1. This is more than the rating of this neighbor, whose rating is 0. So this child, however many candies it gets, it must be more than this child, right? Same thing with this child. Since it's bigger than the rating of this child here, who's its neighbor, it must have more candies than this one, right? So the optimal solution is like, okay, give this one the 1 candy to satisfy condition 1, right? Here you want to minimize the number of candies you need to distribute among the children. So it's like, okay, give this guy 1. This one needs to have more than this, so the next smallest number after 1 is 1 plus 1 is equal to 2, so give this guy 2. This one needs to be more than this one, so the next smallest number after 1 is 1 plus 1 is equal to 2. So you give this one 2 candy, 1 candy, 2 candy, 2 plus 1 plus 2 is equal to 5, so that's why you output 5, right? Here, for example, 1, not bigger than any of its neighbors, right? So we give this guy 1 candy. This guy is indeed bigger than this neighbor, so but not bigger than this neighbor, so it's like, okay, this guy had 1 candy, so let's give this guy 1 plus 1 candies, right? This guy's not bigger than any of its neighbors, so we give it just 1 candy. So 1 plus 2 plus 1. So 1 plus 2 plus 1 ends up giving us 4, right? So the way that I did this is like, okay, I was creating a graph where essentially for each index I would make the node at index I essentially point to index I plus 1 if its rating was higher than the node than the child at index I plus 1's rating, right? So it's like, index I, point to I minus 1 if the rating at index I is bigger than the rating at index I minus 1. Index I, point to index I plus 1 if the rating from index I is bigger than index I plus 1, right? So it's like, for example, you would point a node, so I would point to I plus 1 if it was the case that ratings of I is larger than ratings of I plus 1, right? So that's kind of what I'm saying here, right? And same thing with I minus 1. So essentially, the nodes are the indices, and an index will point to another node if its rating is higher, right? So that you cannot create a graph in this way. What I realized though is like every node is going to have at most 2 neighbors, right? Because it's going to be, a single child. You look at its 2 neighbors and you look at their ratings, right? If the rating on the left is smaller than you, then you point to that one because your rating is bigger. If the one on the right is smaller than you in rating, then you point to the one because your rating is bigger, right? But you'll have at most 2 neighbors for each node. Sorry. And also, this will not form any cycles because, as you can imagine, for example, here, this one points to 0, this 2 points to 0. It's like, they both point to it, but like they can't point to each other. You cannot create a circle out of this thing, right? Because it must be about being bigger. If it was like less than or equal to instead of less than, then we would have problems in this problem, right? But since we're using a less than or greater than sign, There's not going to be any back and forth stuff, so this problem forms a directed acyclic graph, so we can use dynamic programming. So what I did is essentially I said, okay, let's compute the number of candies needed for every single child. So let's do it child by child, right? So each child is mapped to an index inside of ratings, and let's compute the number of candy that it needs. So here my DP function, I have a memo table just for recursive caching. I'll say, okay, if index is in my memo, then return memo of index, right? Here I could also just do like, -1 times n if memo of index doesn't equal -1, right? Then maybe I could do something like this just to make my code a little faster, right? And maybe that's what, like, something that might get me to the edge, right? So yeah, so now I'm at 29 ms. So this is what I mean. Like, I can start optimizing the O of 1 stuff to make things a little faster, but it's not too interesting to me. I think this is a clean enough way of writing the code, so I do not mind it. Here, what we'll do is, okay, we're at DP at index. Okay, if we've already cached the result before, return that result. Otherwise, let's grab that child's rating, right? So ratings of index will be the rating of this current child. Now, let's think about how many candies to give this child. Well, the first condition states that every single child must get at least 1 candy. So the result that I return must be at least 1, right? The number of candy that the child at index, at the index that was inputted to this function, this child must get at least 1 candy. So I'm going to initialize res equal to 1 because I'm going to say, this child needs to have at least 1 candy. Now, if its rating is bigger than, the rating of one of its neighbors, then we know, okay, it must have more candy than those guys, right? So for example, case 1, we're going to look at the left neighbor. As case 2, we're going to look at the right neighbor. Let's start with the left neighbor. So first of all, I should first check if index is greater than 0, because if index is equal to 0, right, if your index is equal to 0, then you have no left neighbor, right? So don't even care. Otherwise, what we say is, okay, so if you have a left neighbor, right, if index is greater than 0, and it is the case that the rating at index -1 is smaller than the current node's rating, right, that means your current rating is bigger than your left neighbor, so you must have more candy than that neighbor. But remember, a DP function computes the number of candy that the child at index needs. So let's compute the number of children that the child at index -1 needs, and let's take that amount and add 1 to it, right? If the left child neighbor needs 5 candies, you must have more candies than them, so do 5 plus 1 is equal to 6, right? Do the next fewest amount of candies than the left child neighbor needs. So you'll do 1 plus the minimum number of candies, the child on your left needs, right? And again, this is why it's important to not have cycles, because otherwise, if left dependent on the right, but right dependent on the left, then you're in an infinite loop. But since we're doing your rating must be greater than your neighbor rating in order to need more candy, then we don't have any cycle issues. If it was greater than or equal to the rating, then we would have graph issues. Since it's not, we can just do this. So we'll say case 1 is equal to 1 plus compute the number of candy that the child at index -1 needs. If the result is less than case 1, right? So case 1 is this. So if this happens to be bigger than 1, okay, then update res is equal to case 1. This is always going to be true. So really what I could do is I could just do this. All right, for this one might not always be true, but for this it will be. So really I could do this, and again, it's I get myself here, but I don't care too much about the O of 1 stuff here, so I'm just gonna leave it as is here. But this is just to show if I start doing some of the O of 1 stuff a bit better, I can probably get around here in terms of solution. So I'm not too worried, but that's the point, right? So if you need more candy than the left child, get the number of candy that the left child needs, add 1 to it. And if that number, right, case 1, if the current result is smaller than that case, then set result to that case, right? Because it'll be, you want to minimize the amount of candy, but you must have at least this many, right? So there you go. Otherwise, we'll say case 2, right neighbor. It could also be that your rating is bigger than the right neighbor, and that guy needs even more candy, right? Let's say your left neighbor, you had a higher rating than your left neighbor, so then you're like, okay, I need at least 4 candy because my left neighbor has 3. What if your right neighbor has 10? Then you actually need even more candy, so that you not only have more candy than your left neighbor, but also more candy than your right neighbor because your rating is higher. So first of all, let's check it that we have a right neighbor, right? So if index +1, as long as it's still less than n, right? As long as it's a valid index, okay, that means we can have a right neighbor. And it is the case that the right neighbor's ratings at index I plus 1, is smaller than our current rating. Then let's do the same thing, right? Let's compute the number of candy that the right neighbor needs, which is the index at index plus 1, so dp of index plus 1, and add 1 to that, right? We need at least 1 more than the number of candy the right neighbor has because we have a larger rating than them. Call this in case 2. If our current result is smaller than case 2, then set result equal to case 2, right? Then for caching purposes, we'll say memo of index is equal to res, and then we'll just return our beautiful result here, right? And then at the very end, what do we do? Well, for each child, so return the minimum number of candies you need to distribute to the candies to the children. So dp of I will return the minimum number of candy the ith child actually needs. So let's return the sum of dp of I for I in range n, right? For every single child, compute the minimum number of candies that it needs, and then just take the sum of all those, and that's the minimum number of candies that you need to distribute. So to solve the original subproblem, we'll take the sum of dp of index I for index I in the range up to n, with each index I representing the children at the ith index inside of ratings, right? And that's pretty much it for how I solved this problem. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful, enjoyable, and in your shape or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.